Okay, let's get right into the weeds. We are looking at a paper today that attempts to resolve one of the longest-standing tensions in machine learning.
Right, this conflict between, computationally brutal combinatorial search on one hand.
And the slick efficiency of differentiable optimization on the other.
Exactly. We're doing a deep dive into sequential attention for feature selection. This is by Yasuda and others, a collaboration between Carnegie Mellon and Google Research.
And it's a really rigorous piece of work. They're tackling the feature selection problem, which for our audience is just finding that best subset of K features from a much larger set of D features.
But they're pushing it with a very specific goal. They want to bridge the heuristic success of deep learning methods with the hard, provable guarantees you get from classical sparse recovery.
Yeah, and the core of the problem, the real tension, is in the methodology. You've historically had these two camps.
You have the greedy forward selection camp.
And then you have the soft selection camp, L1 methods, attention-based methods, that kind of thing.
And the trade-off has always been just brutal. Greedy forward selection is, you could argue, the gold standard for quality.
Because it respects residual value.
It respects residual value. It asks, what is the marginal contribution of this new feature, given the set of features I've already picked?
Which is how you capture conditional dependencies. It's how you solve the XOR problem.
Exactly. But the cost,
Yeah.
it's just prohibitive. You're looking at OKD model evaluations.
Which, in a deep learning context where you have to train a whole model.
You just can't do it. Running a full training loop for every single candidate feature at every single step.
Yeah.
It's impossible for high-dimensional data.
So the whole field pivoted towards efficiency. We started using L1 regularization, lasso, or now these attention mechanisms where you learn a weight vector and just pick the top K features in one go.
But there's a huge problem there.
A blind spot.
A huge blind spot. Standard attention methods are independent selectors. They give a score to each feature on its own merit, ignoring what other features have already been selected.
So you end up picking a bunch of features that are highly correlated, high redundancy.
Right. You get features that all tell you the same thing, and you miss the complementary ones that would have given you much more power as an ensemble.
Okay, so that's the setup. This paper wants to design an algorithm that gets you the sequential, conditional nature of greedy selection.
But with the one-pass efficiency of an attention mechanism.
And their solution is called Sequential Attention, or SA.
And the architecture is really quite clever. It's an iterative algorithm. So if you want to select K features, you run the selection process K times in K steps.
But, and this is the key, you're not training K separate models. It's a single architecture with a very specific kind of masking layer.
Correct. So imagine your input vector X. The method introduces a set of trainable parameters. Let's call them attention weights, W. These are totally separate from the main network weights.
Okay.
At any given step, say step T, you have a set of features, S, that you've already selected.
And those features in S just pass through to the rest of the network untouched.
Exactly. They're fully on. But for the unselected features, the algorithm takes their corresponding weights from W and pushes them through a softmax function.
Which creates a soft mask.
Right, a soft mask. And then the input features are multiplied element-wise, a Hadamard product, by this mask. So the network sees a scaled-down version of the unselected features.
I see. So the training loop for one step looks like this. You optimize both the network parameters and these attention weights, W, to minimize your loss.
Yep. Then once you've converged for that step, you just look at the raw attention weights, W, for all the unselected features.
Then you pick the biggest one.
You pick the one with a maximal weight, W star. That feature then gets added to your set S, its mask gets locked to 1, and you move on to the next step.
And the sequential part is what makes this work. Because when you're training to find the second feature, the first feature is already fully active in the network.
Precisely. The loss function is now driving the attention weights to find the feature that best explains the residual error, the error that was left over by the first feature.
It's a differentiable proxy for that marginal gain calculation.
That's it. And computationally, instead of D model evaluations per step, you just have D extra trainable parameters. It's lightweight.
Now, if the paper just stopped there, it would be a nice heuristic. Look, it works, but they spend most of their time building a solid theoretical foundation for this.
This is the heavy lifting. They want to prove that this differentiable mechanism is, under certain conditions, equivalent to orthogonal matching pursuit, or OMP.
An OMP is the textbook standard for greedy, sparse recovery in linear models. It has robust theorems and guarantees.
So to build that bridge, they first strip down the algorithm to its linear core. They define what they call regularized linear sequential attention.
Okay, what changes?
3 things, just for the proof. First, they get rid of the softmax. They just use the raw attention weights. Second, they apply L2 regularization to those weights.
And third?
They keep the Hadamard product structure. That overparameterization is key.
And this simplified setup is what allows them to bring in Theorem 1.1.
Theorem 1.1. It establishes that this regularized linear SA is mathematically equivalent to another algorithm called sequential lasso.
And we should probably clarify for listeners, this is not standard lasso.
No, not at all. Standard lasso solves for the whole L1 regularization path at once. Sequential lasso is a greedy process. You solve an L1 problem to find one feature, lock it in, and then solve another L1 problem for the next feature, conditioned on the first.
And the link between their Hadamard product and lasso comes from this known duality, right? That overparameterizing with the Hadamard product effectively induces an L1 type penalty.
Exactly. They show optimizing their L2 regularized attention weights in that structure is the same as optimizing an L1 regularized coefficient vector. So step 1 of the proof is done. Regularized SA is the same as sequential lasso.
But step 2 is where they really break new ground, because sequential lasso has been studied before, but the guarantees were pretty limited.
Very limited. The prior analysis only held if you assumed a sparse signal plus noise model for your data. Very restrictive.
So what Yasuda et al. Do with Theorem 1.2 is prove that sequential lasso is equivalent to OMP in the fully general setting.
General, meaning no assumptions about your design matrix X or your response Y. It even works in the overdetermined regime.
How do they prove that?
It's a really neat geometric argument. It involves analyzing the polyhedral section of the L1 ball.
So this is about projecting the residual vector.
Yes. In the dual formulation of the lasso problem, the solution involves projecting your residual onto a polytope defined by the L1 constraints. And what they show is that for a big enough regularization parameter, lambda, this projection always hits a very specific face of that polytope.
And that specific face corresponds to the feature that has the highest correlation with the residual.
Which is the exact definition of the selection step in OMP. OMP literally just picks the feature vector most correlated with the current residual.
Wow. So they close the loop?
They close the loop. The logic is their regularized SA is sequential lasso. Sequential lasso is OMP. Therefore, their attention mechanism is a theoretically sound approximation of greedy residual minimization.
Okay, so the theory is solid, at least in the linear case. Let's talk about the empirical results. When they apply this to actual deep neural networks, were those assumptions?
Though they obviously don't hold.
Right.
Yeah.
They ran a whole suite of benchmarks, MNIST, isolate, mice protein.
Comparing it against things like group lasso, concrete autoencoders, and even standard adaptations of OMP for neural networks.
And the MNIST results were really telling, especially on that redundancy issue we talked about at the start.
Oh yeah, if you look at their visualization in Figure 5, it's night and day. The standard OMP adaptation for neural nets, it tends to select pixels that are all clustered together. It just picks a blob.
Which is maximum redundancy. If you have one pixel, its neighbor doesn't give you much near information.
Exactly. But sequential attention selected this beautiful dispersed set of pixels. It picked up edges and curves from totally different parts of the digit. It respected that conditional information.
And they also did a sanity check on their core claim, right? That the attention weights are actually a proxy for marginal gain.
Yes, this was critical. They did the brutally expensive calculation of the true marginal gain retraining the model for every single feature and compared it to the attention weights their method learned.
And what was the correlation?
Extremely high. The Spearman correlation was about 0.9 for the first feature, and it stayed high for the next steps too. So it empirically validates that the mechanism is doing what they claimed it would do.
Let's touch on the scalability test with the Credeo dataset. Huge dataset.
Over 3 billion examples. This is where that OKD versus OK complexity really matters. You can never run true greedy selection on Credeo.
And how did SA do?
It ran efficiently, and it outperformed the lasso-based methods, especially when you start selecting larger subsets of features, like more than 15.
They also mentioned it was more stable.
Yes, significantly lower variance across runs compared to the lasso methods. In a production system, that kind of deterministic behavior is a huge plus.
Okay, so this brings us to what I think is maybe the most intriguing part of the paper. It's in their analysis of overparameterization.
Mhm.
We've been talking about this architecture that uses a softmax function to create the attention mask.
Right, the attention part of sequential attention.
But the whole theoretical proof we just discussed relied on a version that stripped out the softmax and used L2 regularization instead. So the obvious question is the softmax even necessary?
And this leads them to a great ablation study. They test all these different variants, L1 normalization, L2 normalization, and the standard softmax.
And the result
They
was
were all basically the same. Statistically indistinguishable performance. All of them worked great, and all of them beat the baselines.
that is a fascinating finding. It suggests that the softmax function, which we often think of as the core of any attention mechanism, isn't actually the thing driving the performance here.
Correct. The authors argue, and I think they're right, that the success is really driven by the Hadamard product overparameterization.
So it's about the implicit regularization.
Yes. The very act of parameterizing the model as, a function of x element y is multiplied by w, just introducing those trainable weights, it fundamentally changes the optimization landscape. It creates a loss geometry that's just naturally biased toward finding these sparse solutions.
Which really aligns with a lot of recent theory on overparameterized networks that gradient descent itself has this implicit bias towards simple solutions.
It does. It suggests the selection power isn't coming from the sharp gradients of the softmax function. It's coming from the multiplicative interaction itself. The Hadamard product structure is kind of preconditioning the optimizer to finding important features.
That's a pretty profound insight for how we design architectures. Maybe we're over-engineering things with complex normalization when a simple multiplicative gate is all you need.
It definitely challenges the idea that you need softmax to do attention. If your goal is sparse selection, the structure of the overparameterization seems to be the main engine.
So let's summarize the contributions. First, there's the algorithm itself. A practical, scalable, state-of-the-art feature selector for neural nets that actually respects residual value.
Second, the theoretical contribution. That equivalence chain from their method to sequential lasso to OMP. That's a big deal for connecting deep learning back to classical theory.
And finally, this insight from the ablation study, that the Hadamard product structure is the real hero here, not the specific normalization function on top of it.
It's one of those rare papers that has something for everyone. It gives the engineer a tool they can use tomorrow, and it gives the theoretician a rigorous justification for why it works.
For anyone out there working with high-dimensional tabular data or ininterpretability, this method seems like an immediate tool to add to your arsenal. The implementation is easy, and those theoretical guarantees give you a confidence that you just don't get from a standard black box attention layer.
I agree. And that extension of the OMP equivalence for sequential lasso is a clean mathematical result that will probably be useful well beyond just this paper's architecture.
Well, that wraps up our deep dive into sequential attention, a really elegant solution to a very old problem with some beautiful geometric proofs backing it up. We'll leave the rigorous proof of the polyhedral section for your own reading time.
It is definitely worth the read.
Thanks for listening.